today we're going to look at geometric series. So we've already looked at what a series is, and we've already looked at arithmetic series. So today we're going to look at geometric series. And one thing to keep in mind is, what is a geometric sequence? Remember, it has a common ratio between each term. And it's also important to realize that there are finite geometric series, right? Ones that end, like you only have 5 terms, and ones that go on forever. So we're actually going to talk about, with geometric series, how to find the sum of an infinite sequence. And with arithmetic, we couldn't do that, because as you keep adding more, it gets bigger and bigger and bigger. Geometric series, we can actually find an infinite sum. So a geometric series is just the sum of consecutive terms, right? This happens to be a times 2 geometric series. If the common ratio is greater than 1, so for example, this has a ratio of 2, right? Times 2 every time. So if the ratio is greater than 1, we have to add larger and larger terms to our running sum. The total can get big in a hurry. Using pairs doesn't do much good in this case, because the pairs have different sums. So we can't use that same formula that we used with arithmetic. Fortunately, there's a shortcut formula for the sum of a finite geometric series. We're not really going to use that because we have calculators, but we are going to use the infinite one that I'll show you in a minute. So it's important to know the difference between diverge and converge. A series is said to diverge if it calls for us to continue adding larger and larger numbers. It will approach either positive or negative infinity. This series up here is diverging. Times 2 every time, it's getting bigger and bigger and bigger, diverging. A series is said to converge if it approaches a number other than positive or negative infinity. So it's converging to the number 3, or it's converging to the number 20. So we're going to look at an example. So let's look at this geometric series. What is the ratio? So a sub 1 is 200. The common ratio is 1/2, right? They're multiplying by a half each time. So this is just having us write out the first 4 sequences of partial sums. The first term is 200. If I wanted the sum of the first 2 terms, I would take 200 and add 100 to get 300. What about the sum of the first 3 terms? 200 plus 100 plus 50 is 350. What about the first 4? 200 plus 100 plus 50 plus 25 is 375. Where are these sums going? So a series converges. So this is kind of a proof of how a series converges. So on this next page, I want to show you this quick proof, just so you know where this formula down here comes from. So you don't have to memorize this, but it's kind of interesting to see where the formula comes from. So I first just want to point us back to what S sub 4 looked like. A sub 1 r to the 0 plus a sub 1 r to the first power times r squared times r cubed. So to write out S sub n, we're going to start that way. So S sub n equals a sub 1 r to the 0 plus a sub 1 r to the first plus a sub 1 r squared, and so on, all the way up to a sub 1 r to the n minus 1, right? Geometric sequence, you raise it to the n minus 1 power. So you might get there, but this is a proof, so you wouldn't think to do this. But now they want you to take this series and multiply through by r. So if you multiplied this times r, you'd have an additional power of r each time, right? R to the first, r squared, r cubed, and so on. So r times S sub n equals a to the first, r to the first, right? I'm multiplying this by r. I'm multiplying this by r. So a sub 1 r squared, a sub 1 r cubed, all the way up to a sub 1 r to the n, right? Because this gets added a power. So now a sub 1 r to the n. What happens if I subtract this top row minus this bottom row? So S sub n minus R S sub n. Well, almost every term is going to cancel, right? A sub 1r to the first minus a sub 1r to the first. A sub 1r squared minus a sub 1r squared. And so on, right? So even these will cancel. There will be an n minus 1 term. This will not cancel, and this will not cancel. So S sub n minus r times S sub n is a sub 1 r to the 0 power minus a sub 1 r to the nth power. Not that you would think to do this, but the next step of the proof is they factor S sub n out on the left-hand side. If I take S sub n out, I have 1 minus r left. Okay, and I'm also going to actually factor out a sub 1 out. So isn't anything to the 0 power 1? So isn't this term just a sub 1? So I really have a sub 1. If I divide both terms by a sub 1, I would have 1 minus r to the n, right? I factored the left, I factored the right. Solve for S sub n. A sub 1 times 1 minus r to the n over 1 minus r. And that is your finite geometric series formula. So if you know the first term of the series, you know the r value, you can plug it in with whatever term you want, and could be the 10th term. If you fill out this formula, you'll get your answer. And then it says, what is S sub n if we allow n to go to infinity? So what if I want the infinite term? Well, what's going to happen when your r value is really small? When your r value is really small, r to the nth power basically approaches 0, right? 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2 is a 0. So you'd have a sub 1 times 1 over 1 minus r. And that is the formula that you need for an infinite geometric series. So that formula is the formula you need. Anytime that you need to use this formula, you could use a calculator. So you might as well use sigma notation instead. The only reason I showed you the proof to get here is because it's a really easy jump to go from here to here. So I'm going to show you what this actually means. But when we were looking at that sequence on the front page, and I was showing you that this was, the first term's 200. When I'm adding up to the fourth term, I'm at 375. You keep adding a smaller and smaller number every time. This sequence actually converges. And so I'd actually like to show it to you in the table of values before I just show you the answer. So my sequence is 200 times 1/2 raised to the n minus 1, right? So if I go to my table, they said the first term was 200, then 100, then 50, then 25, right? See how by terms 9 or 10, you're adding 0 point something? So really, if I added up the first 8 or 9 terms, I would pretty much have the sum of my sequence because I'm adding pretty insignificant numbers. So let's go to math, summation. X goes from 1 to, let's just add the first 10 terms together. 200 times 1/2 raised to the n minus 1 power. 399.6. Let me just change that number to, let's do the first 20 terms. 399.9996. You think it's approaching the number 400? Let's use that formula and find out. It says that I take my first term, which is 200, and I divide by 1 minus the ratio. Isn't 200 divided by 1/2 400? So actually, if I did infinite number of terms of this sequence, I would approach 399.999999, which converges to 400. So I wanted to show you some of these together and work through some examples together, and then have you try the guided practice on the back. So if this is the formula for a geometric sequence, let's write out the first 5 terms and find their sum. So obviously the first term is 4, because anything to the 0 power is 1, right? So 4, and then this is 4 times 0.03. So 4 times 0.03 would be 0.12. And then I'm doing 4 times 0.03 squared. So that's 0.0036. 4 times 0.03, oops, cubed is a really small number, 0.000108. I don't think I'm going to go any further. Let's just add together those 4 terms because it's getting pretty small pretty quick. So what is 4 plus 0.12 plus 0.0036 plus 0.000108? 4.124. I'm just going to round it. And I'm just going to show you under math summation, if I said x goes from 1 to 4, 4 times 0.03 raised to the n minus 1 power, 4.1237, right? Adding the first 4 terms manually or with the calculator. Write the series of summation and verify with the calculator. Find the infinite sum. Take the first term and divide by 1 minus the ratio. And when you type this in, 4 divided by 1 minus 0.03 does come out to about 4.124, right? We hit it right on the head with just the first 4 terms. All right, so what if this series goes on forever? 8, 4, 2, 1, 1/2, 1/4, 1/8. Well, I take the first term, which is 8, and I divide by 1 minus the ratio. I'm multiplying by 1/2 each time. 8 divided by 1/2 would be 16. So on 3, 4, 5, and 6, you're plugging this formula into your sigma notation. So you might want to just pause the video and try 3, 4, 5, and 6 before I put the answers up, just to make sure you know how to type them in correctly. And now I'm going to put the answers up. Math summation, x goes from 1 to 10 of 2 times 0.25 raised to the n minus 1 power. 2.67 rounded. Did you get that? Number 4, math summation. I'm going n is 1 to 15, 3 times 0.75 raised to the n minus 1 power. 11.84 is the approximate. These are all finite. Math summation, x goes from 1 to 8 of 4/3 raised to the n minus 1 power. 26.97. 26.97. And math summation, x goes from 1 to 5, 300 times 1.06 raised to the n minus 1 power. 1691.13. 1691.13. Hopefully you tried them on your own, because it can be a little tricky to put them in the calculator. So try these first before you make mistakes on the next page. Now these are infinite sums. See how they're going up to the infinite term? Well, you can't plug infinity in here. You could plug a big number up here if you wanted to, like 100. But we're going to use the formula. So if the R value is bigger than 1, there would be no sum. But all of these have an R value, right? 0.6, 1/2, negative 1/2. All those R values are less than 1. So what you do is you take your first term and you divide by 1 minus the ratio. 4 divided by 1 minus 0.6. Make sure you put that in parentheses, 10. So this series would converge to 10. I just want to show you, if you had put in like 100, x goes from 1 to 100 of 4 times 0.6 raised to the n power. Oh, I have to put a 0 down here. See how this one says n goes from 0 to infinity, and then that's an n instead of an n minus 1. So just, all right, if I put in 100, it's thinking, but it actually did converge to 10, 9.9999999. So I must have gone far enough that it actually did converge right on the calculator. All right, in number 8, there's no starting value, so guess what? There's a 1 hiding there as my starting term. 1 divided by 1 minus 1/2. 1 divided by 1/2 would be 2. If I plug this one into the calculator just to check, if n goes from 0 to like 100, even though 100 is not infinity, 100 is a big number, of 1/2 raised to the x, that actually did converge to 2. So even if you plug in 100, you're going to get close to what the infinity would be. So this one would be another 1 is sitting in front there. 1 divided by 1 minus negative 1/2, right? Because the ratio is negative 1/2 this time. So it's actually 1 divided by 1.5. If you wanted to do it without a calculator, when you divide by a fraction, you actually multiply by the reciprocal. So the answer would be 2/3. 1 divided by 1.5 is 2/3. So hopefully, all you're practicing is putting sigma notation in the calculator and the infinite sum formula. So on the back page, you've just got 7 questions, and you're going to just send me this back page 156.